This is our first lesson on Unit 1718, which is derivatives of exponential and logarithmic functions. And before you get into this unit, you just might want to review some of the material on logarithms and laws of logarithms that you covered in advanced functions. So you can see here the stuff that you're going to be responsible for, some reading and some possible questions that you can do. We're not going to go over this in class. But when we get to box C and box D, we're going to start working with the derivatives of logarithms. So you might need to know this. But today's topic is going to be, we're going to start by just talking about what is this number E. Okay? Box A of the learning guide gets you to go through an investigation or an activity to figure a little bit about where this number E comes from. What I'm going to do here today is a little bit different. So hopefully between the two of them, you'll get some idea of why this number is important. Okay? And the first thing to note about its importance is basically what I've said right here. E is a special number when it is used as the base for an exponential function. And you've looked at exponential functions involving base E back in grade 11 and again in advanced functions. But we're going to take a particular look at why it's important in calculus here. So just to refresh your memory here, an exponential function has the form f at x equals a to the power of x, where a is a positive constant. So a is just some number. In the two examples here, I've done a equals 2, so I'm using 2 as my base. A equals 10, so I'm using 10 as my base here. So keep in mind that these are different from the power functions that we looked at before, where we had things that were like f at x equals, x squared, where we had a number up in our exponent and we had the variable x as our base. Here it's the other way around. We've got a constant or a number as our base, and our variable x is up in our exponent. And the question that we're interested in is, how do we find the derivative of an exponential function, or a function of the form f at x equals a to the x? The first thing we might want to try here is finding our derivative from first principles. So if we think way back, if we want to find the derivative of a function, we took the limit as h goes to 0 of our function evaluated at x plus h, okay, and we subtracted the function evaluated at a to the x, or at x, in this case a to the x, and we divided that whole thing by h. And then we took the limit as h tended to 0, making that difference between the two of them very, very small. So what can we do with this expression we have here? Well, we're still taking the limit as h goes to 0. We can take this first term in our numerator there, and we can break it apart into two powers. So that would be a to the x times a to the h, just using our exponent rules there. That's still minus a to the x. And this is still all divided by h. Again, we're still taking the limit as h goes to 0. Now if we look at our numerator, we've got a term that is a to the x common to our two terms, so we can factor that out. A to the x times, we got a to the h from the first term, minus 1 from the second term, all divided by h. Now the important thing about this a to the x term is that it doesn't involve h in any way. This does not depend on h. It does not depend on h. Okay? So as we take our limit as h approaches 0, the value a to the x isn't going to change. So we can bring that right out in front of our limit here. So our limit becomes a to the x times the limit as h goes to 0 of a to the h minus 1 all over h. So our derivative here is our original function, a to the x, because we're trying to find the derivative of a to the x, we've got our function, a to the x here, multiplied by this thing, this limit here. How do we evaluate this? Okay. There are probably ways of doing it analytically. I don't know any of them off the top of my head. So we're just going to do this numerically. Okay, we're going to pick a value for a. We're going to pick some values of h that get smaller and smaller and smaller. Okay, so we're approaching 0. And we're going to see what this expression works out to. Okay, so fortunately, I've already done that for us. Okay, we're checking the value of the limit as h goes to 0 of a to the h minus 1 over h. And I picked the values a equals 2 and a equals 3. Now don't worry about copying down this table here, because all that really matters is, as I said, we're taking h values that get smaller and smaller and smaller, and we're checking the value of this limit here. And what you see is that when a equals 2, we seem to be tending towards a value of about 0.693 or something like that. And if we choose a value of a, or a base of 3, okay, we seem to be heading towards a value of 1.0, I don't know, maybe 9 or something like that. Okay? And what we're interested in is what would happen if we chose a value that was in between the two of them, in between a base of 2 and a base of 3. If we chose our base so that it was considerably closer to 3 than it was to 2, we could get it so that this limit was equal to 1. Okay? So here it's something less than 1, here it's something greater than 1. Somewhere in between 2 and 3, closer to 3, that limit will be exactly 1. What number do we have to pick as our base to get the limit to be 1? Well, it turns out, all right, that's just what I've said. This suggests the limit will equal 1 at a equals some number between 2 and 3. What is that number? Well, it's the number e. E is approximately equal to 2.71828, so on and so on and so on. It's an irrational number, so the decimals don't repeat, they don't terminate. But this particular value of e is, if we evaluate that limit, okay, the limit now becomes the limit as h goes to 0 of our base is now e to the h minus 1 all over h. It'll work out to be exactly 1. Okay? And I think that's just what I say in the next, yeah. So e is the number such that this limit is equal to 1. Now, why is this important? If we choose our base to be e, our function is f at x equals e to the x. Our derivative from the first slide was a to the x out front. So since a is equal to e, we've got e to the x times this limit, e to the h minus 1 all over h. But we've chosen this number e so that this whole thing is just 1. So our derivative is just e to the x. Okay? So our function is e to the x. Our derivative is e to the x. And that is what makes this number e important in calculus, because the derivative is the same as the original function. Of e to the x is e to the x, okay? Another way of saying this is that the rate of change, the instantaneous rate of change is, of course, given by the derivative of the function or the slope of the tangent. The rate of change is always equal to value of the function. I should say the value, I'll just say the value of f at x. Okay? So the bigger our function gets, the bigger our rate of change is. So you've heard about exponential growth before in terms of populations, right? The population gets bigger, the population grows faster. Because if we wanted to figure out the rate of change of the population, we would take the derivative, and the derivative is always going to depend on the size of the population. Okay? So it's because of this property that when you take the derivative, you get the original function, that e is sometimes called the natural base for an exponential function. And if we've got an exponential function here, y equals e to the x, we know that the inverse of an exponential function is a logarithmic function. Okay. So the inverse of our exponential function here is log to the same base, so in this case base e of x. And because using base e has this very nice property when we're doing exponential functions, we call it the natural base. The same is true for logarithms. Okay, not the property of the derivative, but the fact that it's often called the natural base. So the logarithm to the base e is sometimes called the natural logarithm, and is given the symbol of, instead of log, of ln, where this is the natural logarithm. So it's not the logarithm that's natural, it's base e that is natural, at least in calculus terms. Okay. All right. And so that's what e is all about.